Why hasn't anyone invented a teleportation device yet? Almost certainly many of you have said this out loud at least once in your life. Let's say while stuck in traffic. If we were able to instantly teleport from one place to another, the world would probably look like this. Teleportation is one of the iconic technologies in science fiction, and much of what was described in old sci-fi has already become reality. And some other sci-fi technologies have not been created yet, but are physically possible. But when it comes to teleportation, to put it mildly, it seems that we won't see it in the nearest future. But wait, you might say, what about quantum teleportation? Well, there are news popping up not only about the teleportation of individual particles, but seemingly even of certain macroscopic objects. And I'll say, well, at first, teleportation there is far from what we usually imagine it to be. And secondly, what is happening now is incredibly far from what we see in science fiction. Today we'll primarily focus not on modern quantum teleportation, although we'll focus on that briefly, but rather on teleportation as depicted in fiction. Instantaneous or near-instantaneous movement of large-scale objects and even people over great distances. Will we ever be able to teleport from one city to another? Or abandon the use of rockets altogether and teleport directly to orbit? And perhaps even to other planets? Or to other stars? How could this be achieved and what challenges exist with this idea? Today we'll talk about that and much more, and my name is Andrei and this is Cosmos Elementary. By the way, welcome to all the new subscribers, and also huge thanks to Fraser Kane, who gave a shout out to my channel in one of his recent videos. The main goal of teleportation is to be able to move quickly from one place to another. And in space, this is a challenging topic, considering the immense distances other stars are currently out of reach for us. So we're trying to devise ways to reduce travel time. It's not certain whether the traditional teleportation would be the best option for interstellar travel. For many, teleportation is probably associated with Star Trek. And there, teleportation was used not for traveling between planetary systems, but for descending to a planet's surface from orbit and returning back up. For interstellar travel, they use a warp drive there, which is another example of a technology that first appeared in fiction. And no, it hasn't become a reality despite what some media might say. But it has been discussed quite seriously by scientists, and scientific papers have been written about it, and some research was conducted. I've already covered warp drives in a separate video. In science fiction, the concept of teleportation emerged long before Star Trek, and let me read a short excerpt for you. There was no reason why matter could not be telegraphed, or, to be etymologically accurate, telepumped. It was only necessary to effect at one end of the line the disintegration of the molecules into atoms, and to convey the vibrations of the chemical dissolution by electricity to the other pole, where a corresponding reconstruction could be effected from other atoms. As all atoms are alike, their arrangement into molecules of the same order, and the arrangement of those molecules into an organization similar to the original organization would be practically a reproduction of the original. It would be materialization not in the sense of spiritualist Kant, but in all the truth and logic of stern science. This is the first known mention in literature of what we now call teleportation. However, the word itself is not used here. Here we see the word telepump. But the idea itself is remarkably similar to what we are discussing today. Can you guess when it was written? In 1877. It is an Edward Page Mitchell short story called The Man Without a Body. The full text of the short story is available online, so I'll leave a link to it in the description. And spoiler alert, in the story, the experiment didn't end well for the experimenter. I think it's fine to spoil stories that are almost 150 years old. And also, the spoiler is basically in the title of the short story, The Man Without a Body. So when the main character was being teleported, the power shut off and his body never materialized, only his head. And the entire story is narrated by that said head. In 1897, a parody science fiction book titled to Venus in 5 seconds was released. The full text is also available online. It seems that here, for the first time in literature, matter transfer is used to move from one planet to another. The inhabitants of Venus used this method to travel to Earth and to explore its surface. The word teleportation comes from the ancient Greek tele, meaning remote or distance, and the Latin portare, meaning to carry, although there are slightly different versions of its etymology that I've come across. The Merriam-Webster dictionary suggests that it comes from combining tele and transportation, but the essence is the same. The word itself emerged much later than the concept, and it was first used by the writer Charles Fort in the book of Dreamt. And further on, the concept of teleportation became quite popular in science fiction. From the movie The Fly, it's the one where, well, spoilers, a fly flew into the teleportation chamber with the protagonist, and then the human and the fly got mixed up, resulting in, well, not a very pleasant outcome. But the idea of teleporting matter was certainly solidified and popularized by Star Trek. While we dream of teleportation to save time, the creators of Star Trek introduced teleportation into the plot to save money. By teleporting the characters from the spacecraft to the planet and back using a beam, they didn't have to shoot much more expensive scenes of launching and flying the spacecraft. In my separate video about the warp drive, we found that physics doesn't prohibit such a possibility. Whether we'll ever be able to create such a technology that allows us to travel through space faster than light, bending and warping space-time itself, that's a big question. Just because something is possible conceptually doesn't mean it's achievable. Certainly not right now. So what's the deal with teleportation? I've already mentioned quantum teleportation. The experiments in this field have been conducted for decades, but it is not quite the same. But can a person, in principle, somehow disappear and then reappear in a different place? Surprisingly, the answer is more likely yes, and that could even happen without using super advanced future technologies. However, it involves some quantum phenomena. I've mentioned before that the familiar depictions of atoms with electrons orbiting atomic nuclei like planets around stars are, well, incorrect. At the quantum level, things start to get weird. We're no longer describing the system using clear bodies and their positions in space. Instead, we are talking more about probabilities. There aren't little balls electrons orbiting the nucleus, but rather electron shells, a specific region around the atom's nucleus where an electron with a certain energy is most likely to be found. And the Heisenberg uncertainty principle tells us that it's impossible to simultaneously know the exact values of certain pairs of particles' parameters. For example, it is impossible to simultaneously know exactly where an electron is located and its velocity. The more precisely we measure the velocity, the less precisely we know the position of the electron and vice versa. This arises from the fact that particles have dual nature, as both waves and particles. As a result, according to strange laws of quantum mechanics, an electron can apparently be in several places at the same time, or disappear and reappear. Michio Kaku writes about this in his book Physics of the Impossible, in the chapter on teleportation. And he also writes that while particles behave strangely at the quantum level, when we talk about macroscopic objects and a huge number of particles, these effects average out, and on large scales we don't see anything strange. Moreover, he writes that there is a non-zero probability that each particle in your body will in unison decide to teleport to some distance. And suddenly you'll find yourself on the other side of the wall or wake up on a different planet. However, this event is extremely unlikely. The lifespan of the universe is not long enough for a quantum fluctuation to randomly cause your entire body to teleport to some other place. And besides, we're not just made up of electrons. Michio Kaku doesn't specify or mention other particles like protons and atoms, which are much heavier than electrons and have different probabilities associated with them. But in general, Michio Kaku concludes that laws of quantum mechanics don't prohibit it. But the probability of this is so low that it is easier to say that it is impossible. In scientific databases, you can find a large number of studies on quantum teleportation of individual particles or groups of particles. But when it comes to teleporting large objects and using it as a full-fledged technology, there's hardly any research. And that's not surprising given the kind of crazy nature of the concept, but I still managed to find something. A comprehensive systematic study of teleportation was conducted for the United States Air Force. Naturally, this doesn't mean they're building teleporters there. It's more of a general overview of the subject, its history, various potential technology options, capabilities, and basic principles. There is quite a bit of interesting information available there. This question is also thoroughly explored in popular science books. For example, in the already mentioned Physics of the Impossible, and also in Daniel Whiteson's book, frequently asked questions about the universe. When we want to discuss teleportation, just like in sci-fi, somewhat seriously, two questions arise. Questions of whether it is even possible, and also ethical questions. At the most basic level, the process should look like this. First, some device scans our body, gathers information about what particles we are made of and how they are arranged relative to each other. Then, this information is transmitted over a distance, for example, in the form of a beam of photons, to the destination. And there, another device uses this information to reconstruct you again, but from different atoms. Well, not you exactly, your copy, but more on that later. First, we can take a naive look at this. We constantly transmit data over distance using radiation. And do we have the ability to scan the person? Well, in a sense, yes. Tomographic scanners scan our bodies with a resolution of up to fractions of a millimeter, while various types of electron microscopes are capable of seeing individual atoms and even manipulating them. At the same time, 3D printing technologies are also advancing, and materials for printing include not only plastics but also living cells. It's easy to imagine that if all these technologies continue to develop, they will eventually reach the required level. But it's not just about the technologies. Firstly, many of you have probably noticed a small issue in this brief description, and I'm not even talking about the copy problem yet. Transmitting information about a person using a beam of light implies that this method of matter transportation would no longer be instantaneous. Even if we set aside the volume of information, although we'll come back to that, and how much time it would take to transmit that volume, we are already limited by the speed of light. We know that the absolute speed limit in the universe is the speed of light, also known as the speed of causality or the speed of information. So by teleporting to the moon, again, setting aside the question of the volume of information, we would appear on the moon at least 1.5 seconds later. On Mars, depending on how our planets are positioned relative to each other, it could take several minutes. And for interstellar travel, it would take years. Even at Proxima Centauri b, we would materialize only after 4 years. And on top of that, to pull off even that, we first need to reach Proxima Centauri by the conventional way on a spacecraft, build a teleportation device there, establish communication, and only then could we start moving between systems. And considering the volumes and speed of data transmission, even with Proxima, it would probably take much longer. So yeah, it doesn't sound very exciting already. Although, as a means of transportation on Earth, where we would move if not instantaneously, but almost instantaneously, it sounds better. And even for the solar system, it's still better than spending months and years traveling in a spacecraft. Is the vacation trip worth such a sacrifice? Here's where the issue of a copy arises. To what scale you would need to scan yourself to recreate an absolutely accurate copy? What constitutes you? If we were to achieve resolution at the level of individual cells and recreate a copy based on this information, would it truly be you? Is you stored at the level of molecules, or individual atoms, or elementary particles? Is it enough to recreate a copy with molecular precision? Here we don't have an answer. Furthermore, if we descend to the level of elementary particles, then the uncertainty principle starts to come into play and perhaps we won't be able to obtain precise information at all. In the version of teleportation that uses massless photons to transmit information, we would at least benefit from the speed of light, because if we were to transport matter somehow, we would move much slower. In general, in such scenarios, during the scanning process, the original body is typically destroyed, and at the other end of the wire, only a copy is recreated, even if it is absolutely identical with all of the same memories. Yes, your friends won't notice the difference. For them, it would look like you just moved from a point A to a point B. You could have started discussing something before the teleportation, pause the discussion, teleport, and then after call them back and continue from where you left off. But the original you essentially died. You, living your life, once stepped into a teleportation chamber, and at that moment when you cease to exist, your exact copy appears. It will remember stepping into a teleporter and everything will seem normal to it. Live like if you played Soma. Imagine, you're standing in front of a teleportation chamber, and you can enter it and quickly transport yourself to whatever you need to be. With the thought that an exact copy of you will appear at the other end, one that will remember these thoughts, reassure you. But essentially, your current life as you know it will come to an end. I guess I'll stick to planes, trains, and cars. In the study I mentioned, there was also a slightly different scenario. Firstly, it specifies that it's not just the arrangement of cells, molecules, or even atoms that's scanned, but the complete quantum information about your body, all the information about every particle and its quantum properties. And besides the scenario where only information is transmitted and your body at the other end is assembled from other atoms, there is an option in which information is collected separately, but also your body is disassembled into its constituent parts. And then they are sent in the form of matter or energy along with the information. And on the receiver side, the information is used to reconstruct you from the original matter. Here it seems like you're being reassembled using the same matter you were originally made of. Although it's not very comforting either. After all, you wouldn't survive such a disintegration, and basically what's the difference? Whether they're original atoms or some different atoms, since particles are basically all the same to each other. In general, no matter how you look at it, the prospect doesn't seem very pleasant. And it becomes quite a significant moral and ethical dilemma. Well, if we're talking about the technical aspect, how feasible is this at all? It's easy to fantasize and say, we'll scan the full information about the person. But how much is this full information? There are actually a couple of estimates here. In this study, the authors attempt to assess it. In our body, there are 10 to the power of 28 atoms. It is 10 octillion, or 10 billion billion billion, or 1 followed by 28 zeros. For each of these atoms, we need to encode at least their position, momentum, quantum states, interactions with other atoms and molecules, molecular vibrations, and so on. If we encode all of this information about one atom in 1 kilobyte, then the full information about the person will be 10 to the power of 28 kilobytes, or 10 to the power of 22 gigabytes. How much is that? Here's a figure I came across. In 2020, there were 59 trillion gigabytes of information worldwide. And that's roughly 170 million times smaller than our quantum information about one person. See the problem? What unimaginable computing power is needed to process such an amount of information, and how much time would be required to transmit it? Well, in this article, an estimate is given that it could take thousands of times longer than the current age of the universe. In another article, they attempted to estimate it slightly differently. Instead of scanning every atom to recreate the body, they proposed to count the information in the DNA, which would certainly be less, but then separately scan the content of the human brain. Here, the result still ends up being thousands of lifetimes of the universe to teleport one person, and that's just for the information. So even at the most basic level, with primitive estimates, it seems completely unfeasible. Yes, we don't know what technologies will achieve in the future, if we achieve any. But if we also consider the ethical question, it doesn't seem like a great idea. And there is also a question whether the copy will truly possess all of your knowledge and memories. But what about the teleportation that scientists constantly carry out? That's the quantum one. Well, I won't go into too much detail here. It's a big topic in itself and deserves a separate video. But we can't ignore that completely. Many people, when they see headlines about scientists teleporting a particle or a group of particles, imagine teleportation where the particle disappears in one place and then reappears in another, but that's certainly not the case. In reality, we're transmitting information from one particle to another, and thereby, at the other end, we essentially obtain a copy of the original particle. But we're not physically transporting the same particle to a certain distance. At the heart of quantum teleportation lies the concept of quantum entanglement. It might seem like a strange phenomenon which Einstein called spooky action at a distance. And it could help solve one of the problems of teleportation which I mentioned earlier, the limit on speed. Again, without delving into the details, two particles can be entangled. Two particles can be coherent. The quantum states of such particles are interdependent, and if we have two particles and something happens to one of the entangled particles, it affects the second one as well. Michio Kaku gives an example. Let's assume we have two electrons and they possess a property which is called spin, which in simple terms could be described as rotation, but in practice it is more complex than that. And again, simplifying, spin can be either up or down. Until we measure the particles, we don't know the spin direction, and it's in a state of uncertainty. But when we measure the spin of one of them and find it's up, we automatically know that the spin of the other will be down, even though before that both were undefined. This fact has been experimentally confirmed. And it doesn't matter how far apart these two electrons are if they were initially entangled, even if they were later separated by light years. So it seems like we instantly received information about a distant electron faster than light. But in such a scenario with two particles, it's actually kinda useless. Yes, we've learned the state of the distant electron, but this information is random. We measured our nearby electron and its spin randomly turned out to be up, but it could have been down. So it's similarly random for the second one. The information is random, and we can't use it for transmitting information or superluminal communication. But in modern experiments with quantum teleportation, it's not done like that. They use additional particles that sort of scan the first one, gather information from it, and then transmit it to the third one. And in this way, in broad strokes, it's actually possible to transmit information. But in any case, to transmit the state or information, some ordinary communication channel is used. And in this case, it's still impossible to transmit information faster than the speed of light. The particle itself isn't transmitted, but rather its state. There have been many successful experiments, starting with individual photons, then with photons and other particles, and eventually even without photons at all. There are approaches that utilize a special state of matter called Bose-Einstein condensate. Records are constantly being set for the distance over which particles or groups of particles have been teleported, and researchers are increasing the number of particles involved. In the future, they could progress to large molecules. And ultimately, it seems that there's nothing that prevents us from going from molecules to a full human being. So theoretically, this method used to teleport particles today could be applied to teleport a person, but the same problems we discussed earlier would arise. The original person must be destroyed in the process, and if somehow they are not destroyed, then what? Two copies of you will exist at the same time? The amount of information is immense, the speed is limited. Here, the fundamental possibility of scanning the information about a particle, transmitting it over a distance, and creating an exact copy of that particle is being demonstrated. From there, it's just a matter of scaling up this process. It's theoretically possible, but highly doubtful that it will ever become a reality. And it's unlikely that anyone would be willing to die just so their copy could reach its destination faster. A more likely practical application of quantum teleportation in the foreseeable future is quantum computers and quantum internet. More secure information transmission, which is definitely very cool, but it's not at all what comes to mind when we hear the word teleportation. Perhaps it's better to try to learn how to warp space and master warp technologies, or learn to create traversable wormholes. Sounds busy. Let's get to it.